In this third session on differential equations, we're looking at going even further back and setting up the differential equation before we start solving and finding some answers. So I've got here a question that we're going to look at. Just pause the video for a moment or two so that you can read it thoroughly. Remember how important it is to thoroughly read a question and take in everything that is given to you so you can go on to solve the problem. We're told that the rate of change of radius is inversely proportional to the radius r. And so we're going to write that as dr by dt. Remember that the rate of change of something is the rate of change with respect to time. That may not always be stated, but that will always be true. And because it's inversely proportional, we would write that it is equal to k over r. Now, at this stage, we don't know what k is, but we're given some additional information. We're told initially, that is, when t is equal to 0, the radius is 0.4 centimetres, and the rate of change is that value of 0.25. So we can substitute what we need of those values into our relationship. So the rate of change is equal to k over the radius, which is 0.4. So to find k, we simply multiply 0.25 by 0.4, giving us a value of k of 0.1. That we can substitute back into the differential equation to give us dr by dt is equal to 0.1 over r. And we've now formed the differential equation that we're going to go on to solve. This is a situation where we're going to need to separate variables. So we can take the r across and write r dr, and we bring the dt over to the other side and we integrate both sides. Now we integrate and we find that r squared over 2 is equal to 0.1 t plus c. And again, we go back to the original information that was given so that we can work out our value for c. We were told that initially, when t is 0, r is equal to 0.4. So we have 0.4 squared over 2 is equal to 0.1 times 0. I'll put that in just for completeness, but that gives you a value of c as 0.08, which we can now add to what we originally had. So r squared over 2 is equal to 0.1 t plus 0.08. But what we were asked to do was to find the area when t is equal to 2 seconds. And so we can now use our relationship here to find the radius when t is equal to 2, and then substitute that into our formula for area to find the area. So when t is equal to 2, r squared over 2 is equal to 0.1 times 2 plus 0.08. We multiply by 2 and we'll find that r squared is equal to 0.56 and r is equal to the square root of 0.56. I don't need to evaluate that because when I come to work out the area, I'm going to be using pi times r squared. So that's going to be pi times 0.56, which works out to be 1.76 centimetres squared, correct to 3 significant figures. It's worth taking a moment or two just to think about the processes that we've gone through in solving this particular question. The first thing that we did was to form the differential equation. We took the information that we were given and we had to find the value of k, but we eventually arrived at dr by dt is equal to 0.1 over r. Having found the differential equation, we could then go on to find the general solution. We did that by separating variables, and we arrived at r squared over 2 is equal to 0.1t plus c. Once we'd found the general solution, we used the information given to find the particular solution. R squared over 2 is equal to 0.1t plus 0.08, and then finally, having arrived at that, we're in a position then to use that relationship to find the particular things that we need. And that four-step process is one that's going to become very familiar to you. In this second example, we've told that radium decays at a rate proportional to the amount y that is present at time t. If it takes 1600 years for half the original amount to decay, find the percentage remaining after 200 years. Why not pause the video for a moment or two now and have a go at forming the differential equation yourself. Now this is an interesting question because this key word here, decays, is very important. And what that means is that the amount of radium is going down, and that has an influence on how we record our differential equation. The rate of change will be dy by dt, and because it's going down, we represent that with a negative. We're told that it is proportional to the amount y, so it'll be minus k times y, and that's the differential equation that we're going to solve. Unlike the previous example, we haven't been given any information by which we can find k at this stage, and so we have got to move on to find the general solution and just keep k within the relationships that we find. Pause the video and see how you get on with separating the variables and finding the general solution to this differential equation. How did you get on? We're going to need to move the y across to have 1 over y dy. The minus k can stay, and the dt goes across, and then we integrate both sides. Integrating on the left-hand side, we get ln of y, and on the right, minus kt plus c. We can now use our knowledge of exponentials to write y equals e to the minus kt plus c, and the right-hand side can be split into e to the minus kt times e to the c, and then finally y equals a, e to the minus kt, and we've reached our general solution of the differential equation. In this problem, we've got two unknown quantities, a and k. But one of the reasons for going as far as we did with our general solution is that we know that when t is equal to 0, y will equal a. And so that's the original quantity of radium that we had. We're told that when t is equal to 1600, y is equal to half of that amount, a over 2. And we can now use that to go on to find our value for k. So a over 2 is equal to a e to the minus 1600 k. I've replaced t with 1600, and I've replaced y with a over 2. And in doing that, one of those unknown quantities, a, cancels. That leaves us with a half is equal to e to the minus 1600k. Using what we know from powers, we can therefore write that 2 is equal to e to the power of 1600k. You may need to look at your work on indices if you're not sure about that step. Therefore, ln 2 is equal to 1600k, and k is then going to be ln 2 over 1600, which we can now put into our general solution to find the particular solution. Y equals a e to the minus ln 2 over 1600 times t. And so we've done the first three steps by forming the differential equation, finding the general solution, thirdly the particular solution, and now finally we're going to use the particular solution as we put in the given value of t is equal to 200 years. In that case, y will equal a e to the minus ln 2 over 1600 times 200, which works out to be 0.917 times a. And although we don't know what the original amount a was, we know that after 200 years that is going to be approximately 92% of the original quantity. And we've solved the problem that was set for us to do.